So hello, good morning, everybody, and hope you are having a great time here at INTERGEO Fair in Germany. So what's our menu for today? Let me first a little bit introduce myself. Big data, you have seen that topic, which is a hot buzzword all over currently. And many people look at that from many different directions. I'm going to give you my take, which actually is based on the background of the research we are doing at Jacobs University up there in Bremen, where I'm leading the large-scale scientific information systems research group. And in addition, we have established a spin-off company for commercially supporting what we have developed. And that is our main contribution to society, is the rasdaman system. What that means, that funny word, I will tell a little bit later. And actually, that also brought us into standardization of geoservices. So meantime, in the Open Geospatial Consortium, I'm leading 5 working groups dealing with big data. And I'm editor of more than 12 standards and a couple of candidate standards in this field. I'm contributing to Inspire. And in SQL, in ISO, I have suggested the issue of array SQL, of adding support for big raster data in the SQL query language. OK, but that's just for the overview. So big data, we know that. This buzzword is going all around, and we see so many Vs. Actually, Doug Laney has started that way, way back in 2002, saying that big data means we have high volumes of data, and that's something that definitely applies to geo. So we are having a petabyte of archives, and ESA, the European Space Agency, wants to curate in future 10 to the 12th images. That is 1 million of 1 million images, of 1 million, one more images, that should sit not centrally with ESA, but distributed over Europe. And they are curated, they will be curated centrally by ESA, so that you can access those images as you like. OK, so we have a problem with volume. That's clear, big data. But that's not all. It's also about another V, velocity. We are getting more data than we can hold. Michael Stonebreaker calls this drinking from a fire hose. NASA, EOSDIS, for example, delivers 5 terabytes a day. That's not so much. It's 2 hard disks today. But what if you want to compare those 5 terabytes to what you have done yesterday and the day before and 10 years before? Then we have a problem. Next one, variety. We have a huge amount of different data that all want to go together. We have metadata, we have vector data, we have raster data. We have 2-dimensional raster data, 3-dimensional image time series. We have 4-dimensional weather data. We have regular grids, we have irregular grids. We have a lot of different stuff. And if we would have solved all these problems, we wouldn't need to be here today. So there is an issue. OK, that was what Doug Laney said in 2002 already. IBM added an extra aspect, saying it's about veracity also. Now, what does that mean? It's about the truth, the belief we have in such data. How much can we rely on them? Do we know where they come from? Do we know how they have been processed? Are they accurate enough for our purpose? That is all the aspects that are contained in veracity, and several more. Actually, if you look into the blogs, it's funny. I didn't know that there are so many words with a V in the beginning. You find value, visualization, verisimilitude, and others which people add. I personally still believe that those 4 items define the problems that we have, and the other ones are just ephemerals, are just extra aspects of it. So I've taken this image here as a background for this one because it shows nicely in one particular domain, oceanography, how many data and how variable and different data we have. So just for a visual illustration. And that actually means that scientists and engineers today have a problem. They have to find their data, going through different FTP archives, through different naming schemes. They have to download huge amounts of data just to extract a little bit of it, understand these data, analyze them, and then the real work starts. Don't you think that this is just science? In petrol industry, they are speaking of this department of reformatting as making a joke about a department whose sole purpose is reformatting data so that they can use it. And they also say, hey, we have more bytes today than barrels. So this is really an industrial challenge. So this 80-20 ratio is something that we would like to turn around. What if you have just 20% of time to do all those data preparation and you can use 80% for what you really want to do? That is something that should be achieved. Now, we are living here in GeoWorld, and there we find the OGC standards for the Open Geospatial Consortium. We know all that the basic entity, the basic object is a feature, something that exists, has an identifier, and that can be associated with a location, space, and time. And a special kind of the coverage of the feature is a coverage. A coverage can be called a space-time varying phenomenon, or the digital representation of it. So something that we know as a classical two-dimensional raster image, orthophoto. But there's much more to it. There are three-dimensional time series. There are curvilinear grids. And there are funny grids like those icosahedral ones. Guess what? Coverages contribute the largest part to the big data. So it's fair to concentrate on the coverage terminology when we talk about big data. Looking into the definition that ISO and OGC has, then we find that coverage falls into something that is gridded, with some nomenclature which I'm skipping here. It's strange names, I know. But it continues also with irregular stuff like point clouds called multi-point coverage, multi-curve, multi-surface coverage, multi-solids. So actually there are more objects. Just think about general meshes or triangulated irregular networks. That all falls under this category. OK. So we have a problem of volume and of variety immediately here. How can we deal with that? Well, there is the web coverage service, which is one interface standard which allows us to access such data. Actually, it's a very simple one, focusing at the first and foremost task. I want to read. OK. Was I jumping too much? Okie doke. I guess I changed position a little bit. It can't get worse. Good. OK, risky game here. You know, it's always dangerous to be on stage. So, but up to now, nobody threw a PC at me. So web coverage service, we have too many data, we want to reduce them. So data access. Slicing and dicing, subsetting is the topic. And that is actually what the web coverage service core does for us. It gives us the data unchanged, original, and a subset of it that we want. So very simple, also very simple to implement, tentatively. And so you see more and more implementations, rasdaman, map server, GeoServer, Esri is working on it, Oracle is working on it. So that has a very broad adoption. Extra facets of functionality come in via extensions. Plugins that an implementer can choose or not. So you can differentiate in future products by saying, hey, what extensions do you support? And that allows you to judge whether this tool is the right thing for you. So one problem we have, if we build such a server, we can see here. A climate simulation, for example, the supercomputer will generate the atmospheric condition now, in 20 minutes, in 40 minutes, in 60 minutes, etc. And it will write out data to the file system like this. So in slices. But that's not what we want. If we access those data, actually, we want to have something like, give me the climate over Essen for the last 50 years. Oops. That means the server has to go through all those files, throw away the largest part of it, just to get that small result that we want. Or even worse, if you have an FTP archive, go download yourself and extract. So actually, if we suddenly see that the supercomputer is just one client out of many, we can see that from a different picture. We can say, actually, the server sees different access patterns, a vertical one for the ingest and a horizontal one for the download, and it has to support both in a balanced way. And that is what we do in the rasdaman system, showing you an example that has been done way back already as a precursor for web coverage service. The German Remote Sensing Data Center has taken image of Europe and the Mediterranean, sea surface temperature, has built a large seamless map and extended that over time. So the database contained one large cube consisting of about 10,000 pictures. Okay, we can do a three-dimensional cutout by selecting in space and time via a web interface. You can do a slicing. Any system can do that today. But we also can drill through vertically. Give me the time series over Moscow for 1 year. And now consider the amount of data that goes over the web. It's about 1 kilobyte, as opposed to the big data cube sitting on the server. And therefore, we can be way more efficient. The last one is the vegetation index over the Nile Delta. Actually, the vegetation index, we all know from remote sensing, we can compute that. Why should we store that? We can compute that on the fly from existing data. So what we need is a clever server, an intelligent server, that can do this for us, collecting coverage from everywhere, put them in a server, give us a visual impression, like a web map service, maybe mix in further data, or, by the way, allow other tools to access. So some other computer generates a request and goes there. All of that should be supported. And fortunately, we have the right services away. We have them in place in OGC. We have the sensor observation service, which is cool for capturing pretty much any kind of sensor data that are out there, putting them into standardized coverages, and then taking the web coverage server for download and processing. And therefore, actually, WCS, in spring, I've been invited, or pressed, whatever you want to put it, to write the Inspire download specification in terms of the web coverage service for accessing coverages that are defined in Annex 2 and 3 in Inspire. Our tool, our humble contribution here, is the rasdaman system, which technically is an array database system. So it teaches a standard database system to hold such multidimensional data. To this end, we have married SQL with an image processing language. The whole thing is integrated. You see an example query here. And internally, behind the curtain, we do a lot to make that fast by parallelizing, by having specific architectural constructions. And that's gain us the flexibility of the query language together with the scalability. So it's not just like an API. You have 175 different functions. But whenever you have a new problem, you just write a new query. This is not just experimental, but this is built since 16 years now by us. And it's in operational years since more than 10 years, operational use. And if you want, go to rasdaman.org, and you can download the source code of it to look at it. I will skip that now for lack of time, but I want to show you this one, what you can do with that one. The graphics people, when we wanted to get graphical output, they told us, do you know that a PNG can hold height information in the transparency channel? Oh, interesting. We can render this directly like a terrain if we generate a PNG where elevation is in the transparency channel. Cool, we said. Let's do that. So just for the geeks, take a query that constructs a 4-band PNG image and put whatever you want inside this image. So let's say band 5, 7, and 0 into the red, green, blue, and elevation into the transparency channel. You have to scale it a little bit, and then you get something that can readily be rendered. If you want to see that live, please come to our booth at the Open Source Park, and we will show it to you. Internally, we parallelize those queries, so we break them into pieces and send them out to other servers. But I don't want to talk so much about the technical part. Rather, let me briefly mention Earth Server is our flagship project, which is a large European e-infrastructure project where we do scalable on-demand processing for the earth sciences with 6 application domains where we go to beyond 100 terabytes of data sets. So on ESA data, we do cryospheric services, snow and ice. NASA, no, they don't do satellites this time, but they actually use high-flying drones. MEO in Italy, atmospheric science, climate time series analysis, geology, British Geological Survey, ocean, that's Plymouth Marine Laboratory, and as an exotic one, Mars geology. That all is done based on the rasdaman platform. where all access only via standards conformant interfaces those services. So that can look like this. This is a climate service, and you see the 2D processing and the 1D time series extraction. Ocean color by PML. And die Kartoffeln von unten anschauen, würde man bei uns sagen. Looking at the surface from below. So you see the different stratigraphic layers. That is British Geological Survey, and you are looking at Glasgow from underneath here. So altogether, the big data, actually, it's not new. We had the problems before. The advantage is that now this problem is structured. We know what to look at. We need to deal with volume. We need to deal with velocity, and that's two different things. We need to deal with a variety of data, and we need to deal with the veracity, the trustworthiness of data. Coverages, and specifically raster data, are main contributors to big data in GeoWorld, so it makes sense to treat that. And actually, I have started a big data working group 2 weeks ago in the OGC Technical Committee meeting. So OGC now has a dedicated big data working group. With rasdaman, we contribute a server that has proven to be scalable and flexible to do that. Actually, that is the hits that we have seen on rasdaman since December 30, 2012, so in 2013. And if I manage to convince you a little bit that this thingy is useful, we would be very grateful if you could just step over to Wichmann and drop a card saying, yeah, we like rasdaman, because that would maybe help us to get the Innovation Award, which would be a great award for the team. There are about 20 people working on that, and this obviously is a nice thrust for them. You can benefit by downloading that or by just visiting us at, where was it? Come on, show me. Hall 1, booth 33, Open Source Park. Looking forward to seeing you there. Thank you very much for your attention.